Good afternoon, everyone. I'm Salar Saadatian from Louisiana State University, and I'll be presenting heat and mass transfer in a flat heat pipe with a circular capillary wick under small imposed temperature differences. Heat pipes are highly efficient in transferring heat because they transfer heat by conduction and vapor flow. They have been extensively used for thermal management in a variety of areas, such as in microelectronic components, nuclear reactors, storage facilities, and spacecraft industry. The working principle of a flat heat pipe is shown here. The heat is applied to the evaporator, liquid in the wick evaporates, and the local vapor pressure increases. High pressure drives vapor flow to the condenser where the vapor condenses to liquid, and the capillary pressure gradient brings back the liquid to the evaporator. There are numerous numerical and analytical works done on flat heat pipes. In most heat pipe models in the literature, heat rate through the pipe is imposed as a boundary condition. Here, we solve the heat transfer rate through the heat pipe as part of the solution. Our model flat heat pipe is shown here. The thickness of the wick is D and the height of the vapor region is G. There are NX, NY, and 2 NZ straight capillaries evenly distributed in the X, Y, and Z direction. Capillaries are circular with uniform radius RP and are filled with a liquid. Our model can be used for 2 wick heat pipes, where the second wick is placed on the top plate. This can be handled by using 2N, NX, NZ as the number of pores exposed to the vapor region. The outer surface of the pipe is insulated. Initially, the pipe is at temperature T0. We increase the temperature at one end by delta T and decrease the temperature at the other end by delta T. These end temperatures are maintained until pipe temperature attains a steady state. Heat transfer is one-dimensional, and because delta T is much smaller than T0, the temperature distribution is skew symmetric, and we only study the heat half of the pipe. First, we focus on a single pore. Since the pore size is much smaller than the pipe dimensions, pore level phenomena can be studied locally. We assume that the liquid vapor interface is flat. The local pore wall temperature is Tp, and the local vapor pressure outside the pore is Pg. These pipe level variables can be treated as constant around the pore. Liquid temperature at the interface varies owing to non-uniform evaporation along the interface. At each point on the interface, liquid temperature Ti has a corresponding saturation pressure Pi. Over the heated half of the pipe, Pi is greater than Pg, and this pressure difference leads to continuous evaporation at that point on the interface as shown here, where M is the evaporative mass flux and C is inversely proportional to speed of sounding vapor. We Taylor expand Pi about Pg, and using the Clapeyron equation, we arrive at an equation that expresses the pore evaporation as a function of Ti and Tg.
Due to the small size of the pore, the convective heat transfer is negligible, and the liquid temperature obeys the Laplace equation. At the liquid vapor interface, the required heat flux to convert liquid into vapor is supplied by the conductive heat flux through the liquid. So we have a mixed boundary condition on the interface. We define a set of pore level dimensionless variables to solve the Laplace equation. Parameter E appears in the boundary condition on the interface. We call it the evaporation number. In heat pipes, E is typically large. In the large E limit, the boundary condition on the interface leads to 0 temperature at the interface. However, the interfacial temperature must jump to 1 at the pore edge. As a result, an inner region exists near the pore edge in which the interfacial temperature varies smoothly from 1 to 0. We define a set of dimensionless inner variables and rewrite the Laplace equation and boundary conditions. In the inner region, the temperature gradient term is retained in the boundary condition on the interface. The Laplace equation in the inner region, along with the boundary conditions, is solved by Rajmi and Wong, and the interfacial temperature is found as shown here. By integrating the interfacial temperature along the interface, the dimensionless and dimensional mass evaporation rates are calculated. We divide the pipe into rectangular cells, each containing a single pore. We perform a mass balance on the unit cell and find this equation that relates the variation of a vapor volume flow rate along the pipe to the pore evaporation rate. Therefore, we have brought a pore level result up to the pipe level. Performing an energy balance on the non-vapor region of the unit cell specifies that the conduction heat entering the non-vapor region supplies the evaporation at the pore, and the remaining heat then exits the non-vapor region. This is one-dimensional heat diffusion equation with a sink that connects a pore level variable, MP, to pipe temperature, which is a pipe level variable. Assuming laminar vapor flow, performing a momentum balance on the vapor region of the unit cell shows that the vapor pressure gradient varies along the pipe owing to non-zero evaporation rate. These two equations show that the pipe temperature and vapor pressure are coupled with the mass evaporation rate. The implicit dependence of MP on PG can be made explicit by expanding the vapor temperature about the equilibrium temperature. Using the Clapeyron equation, this time at the equilibrium temperature, we can write the mass evaporation rate as a function of Tp and Pg. The first term inside the bracket is much larger than the second term, so the pressure, vapor pressure can be dropped from the mass evaporation rate equation, and we get the mass evaporation as a function of pipe temperature only. Now we are ready to solve for the pipe temperature. We define a set of pipe level dimensionless variables and rewrite the energy equation. We get a second order linear ordinary differential equation that can be solved with these boundary conditions. S is a dimensionless number that provides a pipe length scale, and its physical meaning is the ratio of heat transferred by evaporation to the heat transferred by conduction. For heat pipes, typically S is a large number. Pipe temperature plot demonstrates that for small s, heat is mainly transferred by conduction, and as S increases, evaporation dominates, and the temperature drops rapidly within a boundary layer of order 1 over S near the hot end. We can also solve for the mass evaporation rate. After dropping the vapor pressure from the mass evaporation rate equation, it simply equals the pipe temperature. We also find the dimensionless vapor volume flow rate and the dimensionless vapor pressure by non-dimensionalizing the mass and momentum balances. The plots of vapor volume flow rate and the vapor pressure confirm the existence of a boundary layer near the hot end. Outside the boundary layer, the evaporated vapor flows along the pipe with constant volume flow rate. This constant volume flow rate is driven by a constant pressure gradient. To find the heat rate through the pipe, we integrate the energy equation once. The first term is the conductive heat rate, and the second term is the vapor flow heat rate. Q is the constant of integration, which is the total heat rate. Since the heat pipe is insulated, Q is a constant. We make this equation dimensionless, where QC is the conductive heat rate in the absence of vapor flow, and Nusselt is the total heat rate, the ratio of the total heat rate to the conductive heat rate. Since we have already found the pipe temperature and vapor volume flow rate, we can find the dimensionless heat rate Nusselt. As I stated before, in heat pipes, S is typically large. In the large S limit, Nusselt approaches S. We also defined an effective thermal conductivity, and because nozzles is a large number, flat heat pipe operates more efficiently than any of the components alone. In order to apply our model to real-world applications, we convert our wick parameters to porous medium parameters. We begin by Darcy's law that gives the volume flow rate in terms of permeability and pressure gradient. Assuming laminar flow in the capillaries, the total volume flow rate in the wick can be calculated in terms of our wick parameters. Comparing with Darcy's law, we can find permeability in terms of our wick parameters. Porosity is the ratio of the volume of the pores to the total volume of the wick. For an isotropic porous medium, the linear pore density in the X, Y, and Z directions should be the same. Therefore, we define a linear pore number density N, and consequently, we are able to find the pore radius and linear pore number density in terms of permeability and porosity of the porous medium. In conclusion, we studied the one-dimensional heat and mass transfer in a flat heat pipe of a rectangular cross-section. The temperature difference delta T was applied to the ends of the heat pipe. We integrated the evaporation kinetics with the heat conduction equation to capture all the essential physics. Heat transfer was solved as a part of solution, which enables us to optimize it by varying the pipe length or wick thickness. And we found that heat rate through the pipe depends on only one dimensionless variable, S. I would like to acknowledge the experimental study done by Sun and his colleagues, which motivated our model. And I would like to also thank my advisor, Dr. Harris Wong, for his guidance and constant support. I'll be happy to answer your questions.